Ladies and gentlemen, boys and girls, thank you all very much for coming. It's just gone 1700 hours here in the UK. It's 1900 in Moscow, and it's 9 a.m. on the West Coast. So good afternoon, good evening, and good morning. My name is Martin, and over the next 30 minutes or so, I will walk you through the advanced pub sub capabilities of Diffusion. I will introduce the concepts. I will show you them working, walk you through some working code, and I will share it all with you on Observable HQ. As many of you will know by now, this webinar is part of a series, each tackling a concept that you, the developer, will likely encounter in the development of your solution. Put your questions to me through the Q&A feature, and I will answer them throughout the presentation. If I don't know the answer, I will get back to you with a considered answer. What I won't do is give you a load of baffle gab, an otherwise thoroughly wonderful word, but you won't get any of that here for the next half an hour or so. So let's quickly recap what we learned in the prior PubSub webinar. We're going to start with the fundamental unit of everything, the topic, which has a path or a name, it has a type and a value. We can usefully think of it as a remote variable or a variable in the cloud. They can hold simple values like numbers or more complex values like strings or JSON values. To consume the value from a topic, we subscribe to it, and the value is delivered to us. Permission allowing, a publisher can update the topic value, after which the subscriber is immediately delivered the new value. We covered how the system achieved high efficiency by transmitting deltas rather than complete values to transmit value changes. We covered stateful and stateless topic updaters, their use cases, and how the convenient stateless topic updater depends on the diffusion server to calculate the value delta, whereas the stateful update mechanism calculates the delta on the client, taking load off the server and transmitting smaller deltas into the deal. The stateful updater is the clear winner when you have a lot of data to publish. Here I'm going to focus on the third method, partial update. The key difference and advantage of this is that whereas stateless and stateful updaters update the whole topic value, we can use partial updates to update part of the topic. This can be very useful when the topic value is too large to be practically stored in the client, or the topic value is updated and owned by more than one source. Imagine a topic holding the most competitive odds for each of the tentpole sporting events for a weekend. Each of the odds from football, rugby, horses, Formula One might come from different teams within your organization. Each team can use partial updates to exclusively update their section without overwriting anything else. Additionally, there are times when you receive only delta values from your back office, which are easily translated into partial updates. If you didn't have a partial update feature, you'd have to retain a value model in your client and probably use the stateful updater, increasing both solution complexity and also memory costs. Partial update can be used only with JSON topics and follows the JSON patch standard, which we're going to dip into a little now. The identifying characteristic of partial update is that instead of sending a completely new value, we send patch instructions to the server. For example, to insert a new value before the second element of the biscuits array, we could use this JSON patch. This will remove the first element of the biscuits array altogether. The replace operation will, in this case, replace the value of the name field of the first element of the biscuits array with chocolate digestive. Copy, as you can imagine, will copy a value from one place to another, and move will effectively rename part of a JSON value. Finally, and most interestingly, we can use the test operation to test equality of part of your JSON value against a JSON literal. On its own, the test operation has no direct effect on the output. However, we can use it and all other operations in combination. For example, imagine we have this JSON document, again with the biscuits. This JSON patch, when executed on the server, will atomically replace the name property of the first array element only if it is currently digestive. Some of you may recognize this looking a little bit like compare and set or compare and swap operations, which are common in high-performance computing. Moving on to update constraints. Now, we use update constraints in combination with existing topic update APIs to constrain topic updates. Importantly, they are atomically constrained such that the topic constraint is evaluated and the update is performed as a single server-side action. For example, given this numeric topic, a topic updater can send an update to the server, which we can read as, if the value is 42, set it to 43. If the value is not 42, the update will fail, and you'll be notified of that failure. It can be tempting to fetch the topic value and check the constraint in user code, but this makes for data races, as the topic value can change after its value is fetched, but before it can be updated, meaning that the last update wins and data is lost. So to build on the prior example, imagine we now have two clients updating the same topic. If our updater fetched the current value, however, before it can apply an update, updater 2 decrements the value to 41. And shortly after that, our original updater then applies the new value of 43, ignorant of the most recent change and thus losing data. This is a classic race condition and one that an update constraint elegantly solves. As we've seen, update constraints can assert that a topic holds a known value. Another type of update constraint can assert that a topic holds no value, or that even no topic is even bound at that topic path. The topic does not exist. Or that a session holds a given session lock. And we'll see a little bit more about locks in a short while. And somewhat like the JSON patch test operation, this update constraint will check parts of the JSON value held on the topic being updated. This constraint will constrain an update to only a topic holding the field foo with the value foo and that has no bar property. Finally, we can compose constraints as well. For example, assert that a topic is locked and holds a known value. Moving on to session locks. Now, session locks are mechanisms managed by Diffusion to coordinate access to shared resources amongst multiple sessions. A session can acquire a lock identified by a lock name. Once the session acquires a lock, no other session can acquire the same lock. On its own, holding a lock does nothing for your session. It grants you no extra permissions. Instead, you use them in combination with an update constraint to assure topic update exclusivity. Locks can be explicitly released, and they're also implicitly released when the session to which they belong are closed. Here's an example of how a lock can be used. So firstly, this call to session.lock will fail if the lock cannot be secured. And then we build the constraint. The final section is familiar to anyone who's used the stateless update API, session.topicupdate.set. The final constraint argument is the new addition that will fail this call if the session no longer holds the lock. Notice that locks are advisory and that holding a lock doesn't mean that somebody else won't update your topic if their code does not bother to secure the lock first. Here's a question for you. In this example, why would you not hold the lock in that final call? And the answer is because locks have session scope by default, but they can have connection scope. So if in this piece of code, if the session lost its connection after lock acquisition and then reconnected, the lock would have been lost. Moving along, the topic update delivery chain, next to focus on is the topic. We know that every topic has a path, a type, and a value. They also have a set of optional topic properties which influence their behavior. A little like session properties, they're established at topic creation and they are immutable thereafter. Unlike sessions, there are no user-defined topic properties. The set of topic properties are publish values only. Now, this disables server-side delta calculations, and it's ideal for scenarios when you know that subsequent topic values bear no relationship, and there's no value in attempting to calculate the topic delta. So this shortcuts the attempt to calculate the topic delta. Don't retain value. The topic does not retain its value, it only publishes it to subscribers. So new subscribers will not receive an initial value. They will only receive a topic update when the topic is next updated. Tidy on unsubscribe. So when a session unsubscribes from a topic, any queued updates for that topic are then removed from the queue to that topic. There's a cost for this, but it can be required by some use cases. The next three topics govern behavior of the time series topics, which I cover in more useful detail in my time series webinar. And validate values. Now, if this is set to true, it will reject updates that would otherwise create invalid instances of that topic's type. Again, it's not free, it has a cost, but it's more usually done on the client. But when you need both belt and braces to make sure that the content is valid, then this is one of your options. So we're halfway there. Now, conflation. This will let you set the conflation policy for this topic. And we'll cover what conflation is shortly. It's an important part of the product, and it's powerful to know how to configure it. Moving on to compression. Everybody knows what compression is. When topic updates are automatically compressed, this topic property governs the level of compression. The owner property that's used by the security model when interpreting permission settings, and removal relates to automatic topic removal, and we'll go into this in a little more detail shortly. Persistent. Now, this can be used to disable persistence for this topic, which you may use in scenarios where the shelf life of a topic's value is so short that it's not worth the cost of persisting it. You might like to use this in combination with don't retain value. So it's ideal for situations where the shelf life of your data is now and not in the future. And finally, priority, which can be set to low, default, or high, and it's used to prioritize updates being sent to a subscribed client. Some of these deserve extra explanation. Let's focus on conflation first. So recall this diagram of the delivery of topic updates for subscribers. Focusing on the delivery side, every topic value update is delivered via a bounded queue held in the Diffusion server memory, so it's finite. Most often, value updates are encoded as deltas, as we can see here. However, if the server needs to make space in the queue or transmit less data to a subscriber that isn't consuming as fast as updates are produced, it can conflate the deltas together. For example, imagine this JSON value holds two named counter properties. A is incremented twice and B is incremented once. The set of deltas resolve to these, setting A to 2 and then to 3, and then incrementing B to 2. Conflating the deltas together gives us this grand delta, which will transform the first topic to the last. Transmitting and applying the conflated delta more efficiently communicates the current value at the cost of lost information. In this case, the value of field A was once equal to 2. Conflation is enabled by default. However, if this is incompatible with requirements, you can disable it with a little bit of code like this. The other topic property I'm going to linger on is removal, which governs the automatic topic removal feature. Using ATR, as it's often known, we can specify the conditions under which a topic and/or other topics will be automatically removed by the server. This gives you the freedom to push as many topics as you need into the topic tree without the worry of removing them so that you don't then run out of memory. It's done when you create the topic and you give it the removal topic property. For example, this ATR policy will remove the topic after this time has elapsed. This will remove the topic if no one has subscribed to it for 5 minutes, or if it's not been updated for an hour, or when the session that created it terminates. We're just scratching the surface here, so have a look at the documentation and examples for more details. I made the same point in the prior webinar, for which I might almost apologize, but I will bang this drum until more people see the value of this feature. It genuinely is the closest thing to garbage collection for your topic tree. ATL policies are certainly easier than removing topics in your code, but again, they're not totally free. When you naturally add whole branches of topics as a unit, consider using a single ATL policy to remove that branch rather than removing individual topics. Next feature to cover is fetch, which is a big one. So recall this diagram. Aside from subscription, we're also able to fetch a number of topics using topic selectors and other criteria. This is clearly useful in scenarios when we want to get one response. And without fetch, we'd have to subscribe, receive one value, and then unsubscribe. And that would create undue effort and wasted computation on the server side. However, fetch offers much more than that, because using fetch, we can optionally fetch the topic specifications. We can choose if we need to fetch the topic values, which may seem counterintuitive, presuming if you're fetching a topic, you would like to fetch the topic value. But using fetch, you can map a topic tree without the cost of getting the topic values, because topic values are usually the largest part. You can limit the number of results to, say, the first 100 or the last 100. Recalling that topic trees can be arbitrarily deep, using fetch, you can limit the depth of your fetch query. You can specify the last result you received as the starting point for your next query, so you can paginate your results. And you can limit your query to specific topic types. Say you only want binary topics or JSON topics or int64 topics. And it's all tied together into a fluent builder interface. For example, this comes straight from the JavaScript examples folder. This fetch request will retrieve no more than 3 topics from any branch that is deeper than 3 parts or steps. It will retrieve the topic properties. It will retrieve only string and int64 topics, and it will present the values as JSON. Remembering that JSON is more comprehensive than just JSON objects and JSON arrays. You can have JSON strings, JSON numbers, JSON null, JSON boolean. And then finally, we press the red button and we execute the query, limiting itself to only topic paths matching this selector. And that's a split path topic selector matching only single character root topics. To introduce flow control, let's go back to this diagram and zoom into the publisher. Topic update requests, and indeed all types of requests, are transmitted to the server. And recalling the conflation slides, responses are delivered via a bounded queue in Diffusion server memory. As the queue is bounded, its finite bounds can be exceeded if more is put into the queue than is taken out. If that happens, the session is closed, which is usually undesirable. Now, flow control is baked into your clients to lessen the chance of this happening. It factors in the depth of any client-side queue, the number of outstanding requests for which a response has not been received, because usually they're in the server-side queue, and the currently active thread. Now, whilst this is currently subject to change, its goal is to signal back pressure to asynchronous clients that could otherwise completely overflow the system. These factors are used to calculate a value between 0 and 1, which is then multiplied by 100 milliseconds, which calculates the length of a client-side microsleep. Practically all API requests beget responses, and all responses are delivered via this mechanism. Note that received topic updates are not subject to flow control, so you can still get your session closed if you subscribe to too much. An ideal system does not suffer flow control, so be watchful of log lines in your server like this, where you're now sleeping for 100 milliseconds, so you can push a maximum of 10 events per second. Excuse me, I said server. This happens in the client because it's the client that gets the flow control. If you do see flow control, here are some of the more common reasons for it. if you're pushing high volumes of data, consider using the high volume connector that's available in the on-premise diffusion solutions. Now, by default, it's on port 8090, but you can configure that in the etc connectors.xml configuration file. You can deepen the associated queue if it makes sense. The high volume connector uses the large queue, which holds 100,000 messages. Extending resources can sometimes conceal an underlying design problem. So be certain this is reasonable, though I have seen solutions that push millions of topic updates, say at topic tree construction time, so it's not unknown. Ensure that your server is not struggling. RAM pressure or thread contention will lead to bottlenecking response delivery. So check for non-default max heap sizes. So remember, a JVM will use by default only 1/4 of the physical memory in your machine. Check also for a sympathetic number of multiplexers. Java Mission Control is very useful in situations like these. More radically, consider sharing the workload. You can have the client do some of the work with update streams, as we've mentioned before, or you can distribute your work across multiple sessions, which will share the work across multiple server-side threads. If you're pushing topic updates for football, for tennis, and for F1, if one session's bottlenecking in flow control, consider using 3. So enough talk. Let's get to the code. Let's quickly take for any questions if we've got some. Okay, we've got some already. So we've got one from Alan. How do I remove a branch of topics with a single ATR policy? That's a good question. And we saw in the examples, you can say when criteria is met, and by default, it will remove just the topic it's associated with. You can say when criteria is met, remove and a selector. So you can say when topic A, nobody has been subscribed to it, or when 12 noon has passed, remove not just topic A, but topic A / or question mark A //, and that will remove the whole branch. And that makes for a much happier server as well, because it can more radically prune the topic tree if that topic branch makes a logical whole. Okay, that's done that. Aside from responses, what other types of messages are delivered to clients via the queue? All messages are delivered via the queue, but broadly speaking, the ones that you're going to see the most are typically topic updates. If you've subscribed to a topic and that topic's been updated, then the topic value update is delivered to you, and there's no way of flow controlling that. What the flow control relates more typically to request responses. So when you're interacting with the server through some other part of the API. And it's something to be wary of, because that's not an issue that flow control can address. If you subscribe to more topics than your bandwidth will allow, then hopefully Conflation will come to your rescue. But if that's not going to happen, then your session is going to get disconnected. Okay, right. Good. Let's have a look at some code, which is my favorite bit. Okay, so as usual, my code is here on Observable HQ. I commend it to you if you work in JavaScript or TypeScript. This is a great place to get things started and to share your ideas. First one we're going to have a look at here is the partial update example. So you'll recall that partial update allows you to update part of the topic. And this is a smart little minimal user interface where we can compose our JSON patch and then apply it and see whether it works or not. So by default, it's going to work with a topic called my JSON topic. I'm just going to click on create. Constraint has been failed because it already exists. So that's ideal. In fact, it's failed for the right reason. So I'm just going to, let's have a look at that topic. There we go. JSON topic value 12. Let's subscribe to that. There we go. What I'm going to do is I'm going to, I don't know anything, or this client on the left knows nothing about it. So I'm going to put something in the football, and I'm going to put some content in there. Good old Lorem Ipsum. And the instruction, you can see that is one operation to add to the /football field. And then we click apply patch. We can see that that operation has succeeded. We've now got two fields in here. But we can do more complex than that. We've got a tabbed interface here, so we can interact. We can use all of the features of JSON patch, which is quite nice. We can play around with it, get to grips with what it can do. And if it succeeds or it fails, it will tell you why it has failed. So let's try something here. So why don't I try and get rid of that, so we can edit all this. So you can see the value is currently 12. Let's use a test operation. So /value, if the value is 10, for example. And that's going to put in a string, which we need to change to a number. And then if the value is 10, set the value to 11. Replace. Now we're expecting this to fail because the value is not 10. The current value is currently 12. So this would implement an atomic increment. So let's apply that. And it's failed. It says patch failed at operation 0, which is exactly right. That has failed because the value is not 10. The value is 12. So reset the value. Presume the value is 12. Set it to 13. Apply that patch. And voila, you actually saw it change. So let's have a look a little bit into the code. For the curious, this is the place where we build the user interface. We do it in 2 steps. We compose the larger pieces here, the text editor, the buttons, we wire them together. And the second function, build patch controls, is the tabbed controls on the top. For each of these of add, remove, copy, move, test. And we compose them together. This is a utility function, so we can create the topic when we need it. And when it is created, we specify that it is given the empty JSON object, so we can start working straight away. And there is also, we're using an update constraint there. We specify that the topic must not exist. It is an exclusive creation. So we don't overwrite anything that, or we don't fail silently here. Now, this is just simple model building. So when we add fields, add an operation, we update the user interface, update the text editor correctly, and we also extend it to be as long as it needs to be. This is really where the magic happens. Oops, look at me. I've left a debugger statement in there. That's lazy of me. This is where the magic actually happens. In fact, it's just this line here where we call session.topicupdate.apply JSON patch to a topic path with the patch object. And if it fails, it'll either throw an outright failure for larger reasons, or the operation may fail because an individual operation has failed. And if that's the case, it will tell us the number of the operation. We saw that happen exactly there. So we can see that to actually perform a topic update, very minimal code. And this is where we establish the session and a set of dependencies. So let's just republish that whilst we're there. Okay. So that's partial update. Have a look at that, play with that, work with that. This is a fairly good place to get code under your fingernails. Now, moving from the next one, building on the example of the update constraint. This is an atomic counter There's a little bit of blurb in there explaining it to us, but it's worthwhile covering this off. In high performance computing scenarios, it's not so common to lock a resource, set the value for the resource, and then unlock the resource. That's referred to often as pessimistic locking. Optimistic locking is a far more performance solution whereby the value of the resource is read. Some computation is done to it. Let's say we add a number to it. And then we write to the resource with not just a new value, but a constraint that must be satisfied. That similarly to what we saw before, we can say, I believe the last time I read you, the value was 7. I wish for you to be 8. And the resource will execute that or not. And this is known often as compare and swap or check and set. But what we have here is an atomic counter, which uses a topic as its shared state. So you can implement atomic counters, not just inside a single process between threads, but as a shared topic amongst processes around the internet. This is using a topic here called my counter. You can see the value is currently 28. This counter, last time it was used, believed it was 26. Well, when it was just loaded, it was 26. So let's just click this again. This should go directly to 29. And indeed it has. In fact, if we subscribe to this topic, you'll see the value changing. There we go, 29. No great surprises there, but here we're going to do that. 31. Let's raise the stakes and put it in 2 browsers. There we go. So it is genuinely shared between itself and also between those 2 separate processes, which could be anywhere on the internet. Let's have a little diversion into the code. We've got a little bit of CSS to make things look smart. This function dresses up a counter topic class. There's just a little bit of DOM and CSS applied there to make that look nice. This is the counter topic class. It's an ES6 class. We've got a builder function, and we've got a private constructor. I much prefer using builder functions over constructors in situations like this. For a couple of reasons. Builders have much more leeway in what they can return. A constructor can only return a constructed object, and sometimes it can throw an exception, but exceptions are problematic. They're also not always very performant. A builder function, on the other hand, can return an object, or it can return a totally different object, or it can return null, or it can throw an exception. So sometimes it can return specialized objects depending upon the scenarios. And in JavaScript land, of course, you can also have asynchronous functions, whereas you cannot have asynchronous constructors. So this is the code where we, first of all, we create the topic, we set the value if it doesn't already exist, and then we build the new object with the constructor. This is the asynchronous part, which is why this is asynchronous. And we catch any exceptions and map those back. Importantly, this is the increment function itself. And you can see here it's building a patch, a JSON patch. And as we saw before, the first operation is a test, which expresses roughly, I believe the value was, when we last spoke, the value was X. I wish you to set it to X plus 1. And if that fails, well, if it succeeds, that's fine. So it'll apply the patch there. If the operation succeeds, then we carry on. If, however, it fails, we get the current value using fetch, and then we iterate through this again. When that succeeds, eventually the value is stored in the value property, which is exposed through the known value getter. Now, in theory, this means that this could iterate indefinitely if you have enough clients trying to iterate that particular topic, in theory. So this is always the compromise we have for high performance computing. For something more realistic, you may want to put in maybe some sort of back off algorithm or some limit on the number of iterations around this loop. Okay, so that is the atomic counterexample. I'm going to just move on now to the last one, which is the fetch demonstration. We saw fetch used briefly in the last example. So a client can fetch requests for the topics and the values for a range of topics. And what we have here is a nice user interface where we can, this is just listing, I think, the first 10 topics in a fetch expression. And if we click on an individual topic, it will use that as the next topic to iterate, to retrieve its page of values from. So I'm just going to pick the last one here, which is myFX USD to CAD. You'll see that the value there changed. And we've retrieved the next set of topics. Now, the depth of the topic values is academic here. You can see the types become a bit more variable here. We've got JSON, double, time series. And time series, we can see the properties get quite interesting because every single time series topic automatically has these three, which is the time series retained range, the amount of data it retains, the subscription range, which is the amount of data which is given to subscribers the first time that they subscribe, and the time series event value type, which in this case, as you can hear, is a string. So we can say this is a time series of string, and you can see the first value there, which is a bit of lorem ipsum. This is a time series of JSON. We can see the values inside there. And as we click on them, page through the topic tree. There we go, until we get to the end. I just kind of reset that. We'll go back to the beginning. And I'm just going to drill into my I can give it a topic selector, so I can be specific about which topics I want to know about. So say my TS. There we go. So I've gone directly to one branch inside the topic tree. I don't care about anything outside of that. Now, in this case, I'm getting both the topic, the specification, which I get the properties from. I'm also getting the value. I don't have to, but let's have a look a little bit into this code. This is really where the heavy lifting is done. So this is where we compose the fetch response, the fetch query. So we build our fetch request. We're just getting 10 at a time. We're getting them with the values presented as JSON. Remembering, although we're getting doubles and strings, those can be presented as JSON. And we're also getting the properties as well. If the from topic is specified, then we will also pass this to request.from, which is the topic within which the topic tree we wish to start fetching. And that is how we paginate. So paginate from. So from topic is this property here. Let's just edit that. So this is a view of from topic. That's almost worth pinning. We render it as a table. There's a bit of HTML DOM jiggery pokery here, and here we're handling time series objects, which need a little bit of different handling. And here we just establish the session. So there's not very much to it. In fact, the heavy lifting is done first off, which is there. That's how we can use fetch. We can use fetch sympathetically with the server to retrieve almost everything from it, because it can be done in pages. And indeed, you can put in pauses between those pages so you don't completely overwhelm the server. Okay, and those are all my demos. Let's see if we've got any questions. Okay, we've got another question. Let's just get to that one now. Right. If I share, says anonymous attendee, if I share my topic updates across more than one sessions, what are the consequences? That is a good question. So topic updates which are applied across a single session are handled by a single thread, and they have a guaranteed to retain causality. So if you update within one session, you update topic A and then topic B, then the topic updates are delivered to subscribers for topic A first before topic B. If, however, you update topics A and B in two separate sessions, there's no causal guarantee. So there's no certainty that updates for A will be delivered before updates for B, even if the update request is delivered to the server beforehand, because each session is typically dealt with by a discrete thread or thread pool. There's no certainty of the execution of that because the work is spread across the available hardware to make it go as fast as it can. And when you're dealing with, for example, discrete sports, so you've got rugby, football, F1, it doesn't matter that topic updates are delivered, that football is delivered asynchronously from rugby. What does matter is that topic updates for the football topic do happen in a predictable sequence. So yeah, you get to spread your work across more hardware, and as long as you think about it, there'll be no problems with that. Okay, that one's good. And we got a question. Thank you very much, Johnny. That's greatly appreciated. Okay, so, okay, no more questions, I think. We've got, so that's a wrap for today. Thank you all very much for coming. We covered today 7 of Diffusion's advanced pub sub features: partial update constraints, session locks, topic properties, conflation, automatic topic removal, and fetch. You can find all of the code from today at this page. Let's just click that. There we go. So it's on my Observable HQ webpage. So have a look at that for you. I'm going to put that into the link in YouTube as well. Speaking of YouTube, be sure to subscribe to our YouTube channel. Click the bell to get the notification when the next video is published, which will be tomorrow. For now, however, thank you all very much for coming. Be sure to come back next month. Thank you.